हेलो एवरीवन। टुडे हम लोग एक नया टॉपिक शुरू करेंगे दैट इज पी ब्लॉक एलिमेंट्स। तो इन 11th क्लास you have gone through group 13, group 14. Now in this series we'll discuss group 15, group 16, 17 and 18. So for these groups we'll discuss the general features, their properties and some of the important compounds. So without wasting our time, we'll just start group 15. So heading will be group 15 elements. These group 15 elements, this is known as nitrogen family, or this is also known as nitrogens. Now why they are known as nitrogens? Because the hydrides of these group 15 are having choking smell. Because of that choking smell of the hydrides of these group 15, they are also collectively known as nitrogens. Nitrogen family, because the first member of this family is nitrogen. So we have these elements. So we'll discuss the features. General electronic configuration. General electronic configuration. Group 15 elements have NS2 and P3. So if you look at this P3, according to Hund's rule, these 3 electrons are occupying 3 p orbitals with same spin quantum number. So this 2p3 is exactly half filled, and this, look at this, when you look at this electronic configuration, this N and this is the valency cell. Now since the electron is entering in the p orbital of the valency cell, this group 15 belongs to the p block. And if you look at this, the valency cell, this valency cell also represents the period number. So the highest occupied shell number represents the period number of that particular group. And the number of electrons in valency cell, we have 5 electrons in the valency cell, 2 electrons in ps orbital, 3 electrons in p orbital. So total number of electrons in the valency cell is 5. And if you look at this, these 3 electrons, these are unpaired electrons, whereas these 2 electrons in s orbital is completely paired. So when we write the electronic configuration of nitrogen family, in the ground state they have 3 unpaired electrons, and these 3 unpaired electrons are occupying the p orbital. Valency cell is N, number of electrons in the valency cell is 5, and the group number is equals to 10 plus number of electrons in valency cell, that is 5. So this is 15 groups. So we have this electronic configuration. After this electronic configuration, we come to the second, that is elements. we have nitrogen, phosphorus, arsenic, antimony and bismuth. These are the elements of group 15. So the first member of the family is nitrogen, so we say this is nitrogen family. Now the metallic character. Nitrogen and phosphorus, this is non-metal. Arsenic, that is metalloid, and antimony and bismuth, this is metal. So the general characteristics, that is on moving down the group, the metallic character increases. So this you are showing the same behavior here. The first two elements are non-metal, the third element is metalloid, and the fourth and the fifth element is metal. That is moving down the group, metallic character increases. So metallic character down the group increases. As the metallic character increases down the group, the electronegativity of these elements will decrease down the group. Electronegativity. So down the group, electronegativity will increase. Down the group, electronegativity will decrease. The most electronegative element of this group 15 is nitrogen, and the least is bismuth. So moving from nitrogen to phosphorus to arsenic to antimony, bismuth, the electronegativity or a tendency to withdraw the shared pair of electrons towards itself decreases. Now if the electronegativity decreases, electropositive character will increase. So I am not mentioning here, though I am already mentioned as the metallic character. So as the metallic character increases, electropositive character will also increase. Now coming to the size, moving down the group, size increases due to addition of extra shell. The radius or the size of these elements increases down the group. So the largest size among this group 15 element is bismuth. As I told you, the increase in size is due to addition of extra shell. Due to addition of extra shell. So as the addition of extra shell increases, the size of these elements also increases. Number 6, ionization energy. Energy required to remove the electrons from the valency shell. Now we are saying moving down the group, size increases. As the size increases, the attractive force between the valency shell electron and the nucleus keeps on decreasing. As the attractive force between the valence shell electron and nucleus decreases, the energy required to remove this electron keeps on decreasing. So due to increase in size, the attractive force between nucleus and valence shell electron decreases. As a result, the ionization energy down the group decreases. So the largest or the element having the highest ionization energy is nitrogen, and the one having the least value of ionization energy will be bismuth. Now after this we have electron affinity or electron gain enthalpy value. Now look at this. These elements in the ground state having half filled stability. So p orbital is having 3 electrons and this is completely half filled. Now due to the extra stability of this half filled element, the electron gain enthalpy values are having positive value, because on addition of electron, the half field stability of the P3 configuration will be destroyed. So to destroy means you have to supply energy. So the electron gain enthalpy values for these elements of group 15 are having positive value, because they won't like to accept electron and is converted into negative. Now moving down the group, size increases. As the size increases, the tendency for accepting electron will decrease, because the attractive force between the valence electron and the nucleus decreases. Now when we talk of electron gain enthalpy or electron affinity values, the value for P will be greater than nitrogen, then we have normal, arsenic, antimony and bismuth. This abnormal behavior is shown by second group and the third group element. Third group, due to the larger size of p orbital, the repulsion factor felt by the added electron will be less. As a result, slightly more amount of energy will be released when this electron is added to the neutral isolated valence shell of these elements. So simply saying, the electron affinity values for this group will be having large positive due to the extra stability of this half-filled orbital. Now, next property of these elements, that is the physical state of these elements. Nitrogen physical state, nitrogen is gas, phosphorus, arsenic, antimony, bismuth. Phosphorus, we say this is a waxy solid. Arsenic, antimony, bismuth, this exists as solid, hard solid. Now look at this, the physical state, that is physical states of these elements. The first element, nitrogen, in the elemental state it exists as a gas. The remaining elements, phosphorus, arsenic, antimony, bismuth, exists as the solid. Now when we say the first element exists as gas and the rest of the elements exist as solid, so in solid the attractive force between the particles is the highest. So as the attractive force is highest, the melting point of these elements will also increase down the group. So when we discussing the melting point, from nitrogen to phosphorus to arsenic to antimony to bismuth, moving down the group, hardness of the substance increases. As the hardness increases, the melting point will increase down the group. So the increase in melting point down the group is due to stronger attractive force that exists in the solid state compared to that of the gas. Then the atomicity or the catenation. So we have the first element, nitrogen. Nitrogen exists as N2 gas, so the atomicity is equals to 2, nitrogen diatomic. Now rest of the elements, phosphorus, arsenic, antimony, bismuth, this exists as, let me give you this as X, so X4, tetraatomic. So atomicity is 4. So the first element, nitrogen, atomicity is 2, so this exists as N2 gas. The rest of the elements exists as X4, that is tetraatomic. Now the question is, why nitrogen does not show tetraatomicity, or why the rest of the elements does not show atomicity too. Now we have to explain. Now look at nitrogen. Nitrogen is having a triple bond. So we have one sigma bond and two pi bond that exist in nitrogen molecule, that is N2. Now nitrogen being the smallest in size of this group 15 element, the size of 2p also the smallest. So we have this is sigma bond, this two is your pi bond. Now this pi bond is formed by 2p overlapping between 2p and 2p. Now look at this. As I told you, nitrogen being the smallest in size, the size of 2p is also the smallest of all the group elements. So the overlapping between 2p and 2p is the maximum, and the pi bond formation is the most prominent and the strongest. So this pi bond formation is prominent due to stronger overlap between small size 2p orbital. So the pi bond is strongest in case of nitrogen. The reason is overlapping between small size 2p orbital is the most prominent or the strongest. Now coming to this, let's compare this P2. Now if P2 exists, then there must be similar to nitrogen, one sigma bond and two pi bond. Now phosphorus is in third group, so the pi orbital should be formed between 3p and 3p. Now the size of 3p orbital being greater than 2p, the extent of overlapping between 3p orbitals and 3p orbital is very weak. As the extent of overlap between 3p and the 3p orbital is weak, the pi bond formation is less prominent in phosphorus. As the pi bond formation is less prominent due to the weak overlapping tendency of this 3p, P2 does not exist or pi bond formation does not take place in phosphorus. If the pi bond formation does not take place in phosphorus, then moving down the group, the size of orbital also increases, then the pi bond formation becomes less and less prominent. So this pi bond is less prominent due to weaker overlap between larger size 3p orbitals. So this is the reason why P2 does not exist. So P2 does not exist because the pi bond formation between 3p and 3p is very poor. So the pi bond formation is less prominent. So P2 cannot exist. If P2 cannot exist, then arsenic, antimony, bismuth can also form pi bond. The only pi bond that is formed is in the case of nitrogen. The reason is nitrogen being the smallest in size, the size of 2p orbital is also small, and the overlap between 2p orbital is maximum. So pi bond formation is very strong or prominent in case of nitrogen. Now the rest of the elements, that is phosphorus, arsenic, antimony and bismuth, exist as X4, whereas nitrogen does not exist in X4. So this X4, the arrangement is tetrahedral, means this 4x occupies the four corners of tetrahedron. So we have, look at this, X, 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 X. Now when this X4 occupies 4 corners of tetrahedron, this bond angle is found to be 60 degree rather than 109. Now look at this. Due to this bond angle being 60 degree, there is a large angle strain. As a result of this large angle strain, this phosphorus is highly reactive. Angle strain, and due to this angle strain, reactivity is large. So the reactivity is large because of this angle strain. Given a chance, you will break this bond so that angle strain is released. So these elements forms this tetrahedral, that is X4, whereas this nitrogen does not exist. Nitrogen does not exist because, N4 does not exist because due to small size, there is a large repulsion between the non-bonded electrons of the inner core. So due to small size, larger repulsion between non-bonded electrons of the inner core, this 9,4 does not exist due to small size, large or larger electronic repulsion of the non-bonded electrons of inner core. Due to small size, there exists a large electronic repulsion between non-bonded electrons. So due to this N4 does not exist. So look at this. N2 exists diatomic because the pi bond formation is very strong due to small size of 2 p orbital. The overlap between p orbital became the more prominent. P2 does not exist because due to larger size of 3p orbital or below these elements, the overlapping between the p orbital is less prominent, and the result pi bond formation does not take place in the higher member elements. Rest of these elements shows X4 tetrahedral, in which these elements occupies the 4 corners of tetrahedron, in which the bond angle is 60 degree. N4 does not exist. The reason is large electronic repulsion. Because of this repulsion, N4 does not exist. So this is how this element exists in the ground state or the elemental state. Now coming to the oxidation state of these elements, oxidation states. These elements shows oxmax. So since the number of electrons present in the valency shell is 5, these elements shows a maximum oxidation state of +5. Maximum oxidation state is +5 due to the presence of 5 electrons in the valency shell. Now moving down the groove, the inner pair effect increases. As the inner pair effect increases, the stability of +5 oxidation state decreases, whereas the stability of +3 oxidation state increases. So we have looked at this: nitrogen, phosphorus, arsenic, antimony and bismuth. So moving from nitrogen to bismuth, inert pair effect increases. So as the inert pair effect increases, stability of +5 decreases and stability of +3 increases. These two elements, nitrogen and phosphorus, being small in size and high electronegativity, shows -3 oxidation state. This is due to high electronegativity and small size, but the rest of the elements does not show it. So we have two oxidation state, +3 +5. Stability of +3 increases, stability of +5 decreases down the group. So this is because of increasing inner pair effect. The tendency for the s electrons to participate in the chemical bonding decreases, or s electron will try to remain inert. So this +3 state of this high member is less stable in aqueous solution and fairly stable in strong acidic medium. So that means, take this, we have bismuth +3. So this bismuth +3, when we dissolve in bismuth +3 in water, this is immediately hydrolyzed and this gives you bismuthyl ion plus H+ ion. So in acidic medium, look at this, when this bismutyl ion reacts with H+ ion, this reverts back to water as well as. So this is stable only in acidic medium, whereas in aqueous medium this is immediately hydrolyzed to give you bismutyl ion. Bismutyl ion. So that is, if we have this BiCl3, now this immediately reacts to give you BiOCl, bismutyl chloride, and this gives you HCl. Similarly, we can have a look at this antimony +3. These also hydrolyze by water and this gives antimonyl oxide plus H. So this +3 is fairly stable in acidic medium. Aqueous medium, this is easily hydrolyzed to give you antimonyl or bismutyl ion. This is oxidation state. Now coming to the covalency of these elements. Nitrogen shows a covalency of maximum of 4. That means nitrogen, due to the absence of d orbital, it cannot expand valency due to absence of d orbitals. So nitrogen, due to absence of d orbital, cannot expand its valency beyond 4. Whereas this phosphorus, arsenic, antimony, bismuth can extend valency up to 6 due to presence of vacant d orbital. So in this way, the first member shows some abnormal behavior due to the absence of d orbitals, and the rest of these elements shows some similarity property due to the presence of vacant d orbital. So the maximum valency, covalency of nitrogen in any compound of nitrogen is 4, and the rest of the elements can have 6 due to absence or presence of d orbital. Now coming to the reactivity of these group 15 elements, as I told you, nitrogen reactivity, nitrogen N2, so we have N triple bond. This nitrogen in N2 elemental state is less reactive at room temperature, the reason being very strong triple bonds. So we require a large amount of energy to break this triple bond. So this nitrogen is less reactive in room temperature. Whereas look at this P4, This P4 is, especially white phosphorus, is extremely reactive especially white phosphorus. I'll tell you later. So white phosphorus is extremely reactive due to large angle strain. And just shown you the structure. This exists as tetrahedral with bond angle of 60. So there is a large angle strain. So given any chance, this will try to remove the angle strain. So this P4 is reactive, but whereas the rest of the elements are again less reactive at normal temperature. That is, they are very hot substance. So they react at elevated temperatures with oxygen. So this is the reactivity of these elements. So these elements of group 15, that is nitrogen, phosphorus, arsenic, antimony, bismuth. So except this bismuth, these elements shows allotropic form. Bismuth does not show allotropic form, and the most prominent of all this is phosphorus. So phosphorus exists in white and red. There are other forms also. So white phosphorus and red phosphorus. So white phosphorus and red phosphorus. White is tetrahedral P4 and the red is polymeric form. So this being polymeric form is less reactive, while this monomeric form P4 is the most reactive. So we say this white phosphorus is extremely reactive and also poisonous. So in many of these organic chemical reactions we use a red phosphorus. We use a reducing agent, so red phosphorus is used. The reason being this is less reactive and less poisonous also, whereas this white phosphorus is poisonous as well as more reactive. So this is the two allotropic forms of phosphorus. So I told you why white phosphorus is more reactive due to angle strain, whereas this form, that is polymeric form, so this exists in this polymeric form. So this being polymeric form, this is less reactive, whereas this is highly reactive due to angle strain. So now coming to the chemical properties of these group 15 elements. First we'll take oxides of this group 15 element. Oxides of this group 15 element. These group 15 elements forms three series of oxides: H2O3, H2O4 and H2O5. This is in +3 oxidation state, +4 and +5 oxidation states. So we have N2O3, P2O3, AH2O3, Sb2O3, Bi2O3. H2O4 series, N2O4, P2O4, AH2O4. So these are the series of oxides. Then we have N2O5, P2O5, AH2O5, Sb2O5, Bi2O5. Now we'll compare the acidic strength, stability of any of these series. Now moving from this H2O3 to H2O5, for any of this element, that is N2O3 to N2O5 or Sb2O3 to Sb2O5. Now from this oxidation state increases. As the oxidation state increases or the percentage of oxygen increases, the electron withdrawing character increases. As the electron withdrawing character increases, acidic character increases. So when we discuss the acidic character of this H2O3, H2O4 and H2O5, H2O5 is the most acidic, H2O3 is the least acidic. So in any given series, acidic character increases from H2O3 to H2O5. Now take any particular series, H2O3 or H2O5. In any series moving from nitrogen to bismuth, that is moving down the group. Moving down the group, electronegativity decreases or the metallic character increases. As the electronegativity decreases, the acidic character will decrease. Acidic character decreases. So in this series, N2O5 is the strongest acid, B2O5 is the least acidic. Similarly, N2O3 is the strongest acid, Bi2O3 is the least acidic. Again, now moving from nitrogen to bismuth in any of this series, as the electronegativity decreases, thermal stability also decreases. So in any particular series moving down the group, thermal stability of that series of oxide decreases due to decrease in electronegativity. Decrease in electronegativity. So these oxides are acidic, but acidic character, how they behave, acidic character varies in a particular series or from one series to another series. Now taking up this, look at this. With H2O3, suppose this nitrogen, N2O3, on hydrolysis, this gives you nitrous acid. N2O4, on reaction with water, hydrolysis, this gives you a mixture of HNO3 and HNO2. Whereas this N2O5, on hydrolysis, this gives you HNO3. Now this N2O5 on hydrolysis gives nitric acid, so this is known as anhydrous of nitric acid. This is known as mixed hydride because this gives you a mixture of acid. Mixed anhydride. While this N2O3, this is known as anhydride of nitrous acid. So that means this nitric acid is a stronger acid than nitrous acid. Similarly, we can take this phosphorus. So P2O3, these on hydrolysis gives you phosphorus acid, and P2O4 on hydrolysis gives a mixture of phosphorus and phosphoric acid, whereas this P2O5 on hydrolysis gives you H3PO4. So look at this is anhydride of phosphorus, this is mixed anhydride. So H3PO4 is more acidic than H3PO3. So this is how we define the acidic behavior of the oxides, and these oxides on hydrolysis gives you various acids, and so these are known as acidic in nature. So if this is the case, then as the oxidation state of the central metal increases, the acidic character of oxide as well as the oxo acids increases. So this is the reason. This is +5, this is +3. So the +5 is more acidic than +3. Similarly, look at it. This is +5, this is +3. So +5 state is more acidic than +3. So this is the oxides. Apart from these, Nitrogen also shows some other oxides. Nitrogen, so let me discuss the oxides of nitrogen here. Oxides of nitrogen. We have formula, name, oxidation state, structure, and remark. So first one is N2O, name is known as nitrogen 1 oxide or nitrous oxide. Nitrogen 1 oxide. Or nitrous oxide, or commonly known as laughing gas. So this is N2O. Now this nitrogen is in +1 oxidation state. Structure is linear. So this nitrogen bond is linear and the bond angle is 180 degrees. Nitrogen bond being the triple bond, this is the strongest or shortest bond, means nitrogen shortest and having largest bond angle. Remark, this is neutral oxide, neutral in character. This does not react with acid as well as base. Then we have NO, nitrogen 2 oxide. Nitrogen 2 oxide, oxidation state +2. This nitrogen 1 oxide structure, this is also neutral. If you look at this is odd electron containing oxide. This odd electron containing oxide is paramagnetic. So this being odd electron containing, this immediately try to undergo dimerization. It immediately dimerizes to give you NO2. This dimer is diamagnetic. So nitrogen 2 oxide is odd electron containing oxide which shows paramagnetic but it undergoes dimerization, but in this dimer there is no unpaired electron, so this shows diamagnetic. This is neutral oxide. Then we have N2O3, nitrogen 3 oxide, oxidation state is +3, structure is we have this nitrogen oxide, these nitrogen 3 oxide, that is +3, is acidic. This is acidic oxide. N is blue color. So we have this nitrogen 3 oxide with this structure. We have a nitrogen single bond. This is acidic and this was blue. So at room temperature, this N2O3 undergoes dissociation to give you NO2. Due to the formation of this into this mixture of gas is brown. So N2O3 at room temperature dissociates to give you NO plus NO2, and due to the formation of this NO2 the color changes to the brown color, from blue to brown. This is blue, now changes to brown. Brown color is due to the formation of NO2. So this is N2O3, which is acidic as I told you. This on hydrolysis gives you nitrous acid, and this being acid, this is known as acidic in character. So we have two neutral oxides. This one is 3. The third one N2O3, which is acidic. Then the fourth oxide is NO2, nitrogen 4 oxide. Oxidation state is +4, nitrogen +4. Structure, so we have an unpaired electron. This is brown color and acidic. Unpaired electron means all electron containing species. Because of this, this is again paramagnetic in nature. So this undergoes dimerization to give you N2O4. So this is dimer. So dimer is diamagnetic because this doesn't have unpaired electron. So immediately this dimerized to give you the dimer, that is N2O4. This is known as the mixed oxide. So the reason is this N2O4 reacts with water when this gives mixture of nitric and nitrous acid. Then we have look at this N2O5, nitrogen 5 oxide. Oxidation state is +5. Structure is, so let me give you the structure of this N2O4. N2O4, this is N2O4. Then we have N2O5, nitrogen, oxygen, nitrogen. This is the structure of N2O5. This is colorless and this is also acidic in nature. This is known as anhydride of nitric acid because this on hydrolysis gives you nitric acid. So these are the various oxides of nitrogen. Their standard name, oxidation state, structure, magnetic behavior, as well as their acidic, basic or neutral nature. These are the oxides of nitrogen. Similarly, phosphorus also shows two important oxides. So let me give you the oxides of phosphorus also. So I'll rub this. Phosphorus mainly forms two oxides. So phosphorus reacts with this oxygen to give you P2O3, and this dimerize to give you P4O6. That is dimer. Then this gives you second oxide, is P2O5, and this dimerize to give you P4O10. That is phosphorus pentoxide, phosphorus trioxide. This is dimer form, this is monomeric form. So these oxides of phosphorus has got this structure, ring structure. So we have to show this P4O6. This forms tetrahedral type with so this is the structure of P4O6. If you look at this, the number of PP bond, that is 0. We have POP bond 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 POP bonds. So this is known as bridging bond. There is no P double bond oxygen bond. This is the characteristics of P4O6. Now coming to P4O10. These P4O10, you have structure similar to this P4O6. So we have phosphorus occupying 4 corners of tetrahedron with POP bridge bond, and each phosphorus is having a double bond oxygen, or we said that is dative bond. So number of PP bond is still 0, number of POP bond remains 6, P double bond O bond is 4, 1, 2, 3, 4, that is also known as P oxygen dative bond. So these are the characteristics of these two. So these on hydrolysis gives you phosphorus acid, whereas these on hydrolysis gives you phosphoric acid. So this is known as anhydride of phosphoric acid. This is known as anhydride of phosphorus acid. This is the structure of phosphoric oxides. So you have to remember the structure, number of PP bonds, number of POP bridge bonds, and number of PO bonds also. Now after these oxides, we will come to the hydrides. Hydrides of group 15. Hydrides of group